Hello everyone, in this video I'm going to talk about solving initial value problems. Of course, we already solved this initial value problems, we already did that, but as you see in the previous videos and previous subjects, we had to find the general solution first, then apply initial conditions. You'll see one of the advantage of this method that we don't have to do that. We can go directly and solve the initial value problem. Other advantages, of course, are techniques that can easily handle equations involving forcing functions, having jump discontinuities, and there are some other advantages. When it comes to the method itself, as written here, you take the Laplace transform to both sides of the equation. Then you use the properties and the initial conditions to obtain an equation for the Laplace transform of the solution, and then solve this equation for the transform. Finally, you determine the inverse Laplace transform of the solution by looking it up in the table we saw, and we're going to expand those tables as well, or by using some method like partial fraction decomposition if needed with the combination of the table. So all the examples I'm going to do in this video have to do with solving initial value problems using Laplace transforms. The first one, second derivative plus the first derivative minus 2 times the function equals 0. The initial conditions are y of 0 equal 1 and y prime of 0 equal 13. So we take Laplace transform to both sides, and you know with linearity it's going to be Laplace transform of the second derivative plus Laplace transform of the first derivative minus 2 times Laplace transform of the function equal Laplace transform of the right side. And if you look up the formula that we did for the second derivative, or also set up as a table as well, for this second one it's going to be s squared times Laplace transform, and all these on s, of course. If I don't write it down, we're used to now on s, right? So Laplace transform of y, of course it's going to be on s minus s times the initial value, the first one there, then the second one there. That's for this. Then now for the next one, the formula that we've seen, s times Laplace transforms of the function, of course on s, minus y of 0, then minus for this other one, minus 2. Laplace transforms of the function is just going to be the function y of s, right? And equal on the right hand side we just have 0. Right, let's clean up these. S squared times y of s minus, we have 1 times s, so s, minus this initial is 13 given, then s y of s, then minus again this initial condition is 1 minus 2 y of s equals 0. Putting the terms of y of s together and factoring y of s, we get s squared minus plus s minus 2 equal s plus 14. So now, sometimes in some exercises you're asked just to find this formula first. So you understand the middle step in the method. And now to go back to the function that we're looking for, we need, and I think also in this problem probably this is what it is asked. However, we need to get used to putting it in the form that we can reverse with the Laplace transform, or use the inverse Laplace transform. So here we will need to do partial fraction decomposition. I'll show you a nice method to use. Let's factor first the denominator, s minus 1 times s plus 2, s plus 14 here in the numerator. This method I will do for fraction decomposition is called Heaviside cover-up. It works well with this type. So let's show you, let's change color here. So as you know, of course, this is going to be two fractions added, and with a over s plus 1 because it's linear, so the constant on top, and same thing for s plus 2 and b there. So to find these, what I will do, maybe I'll write it here so you can see how nice is this method. The critical value here is s equal 1, so if I cover this, I can just plug in s equal 1 in this quantity here, and it will give me a, because a corresponds with the s value equal negative 1. Negative 1, critical value is negative 1. So let's fix it. S minus 1, s plus 2. So yeah, the critical value is s equal 1. So if we have 1 plus 14 over 1 plus 2, that's 15 over 3 is 5. So this is 5. Now let's redo the work for s plus 14, s minus 1, s plus 2. So this is the critical value is negative 2. So you can't, of course, use it there. It will make it undefined. So now if I substitute negative 2, I should get b. So negative 2 plus 14 over negative 2 minus 1, which is 12 over negative 3, which is negative 4. And this is negative 4. Alright, so if I want to keep this in the same page, we can just write the solution here. Not yet in T, just in S. Y of S is 5 over S minus 1 minus 4 over S plus 2. Okay, so let's go back to the method and talk about this. So take Laplace transform of both sides of the equations we did. Use the properties and the initial conditions to obtain an equation for the Laplace transform of the solution, and then solve this equation for the transform we did. Determine the inverse Laplace transform. So now we're going to go into that. Determine the inverse of Laplace transform of the solution by looking it up in the table and stuff. So that's where we are now. We'll apply the inverse Laplace transform on that. Alright, so now you see y of t, we're using the inverse Laplace transform, pi over t, pi over s minus 1 minus 4 over s plus 2, and with linearity, of course, and of course this is on t, right? It's going to be 5 1 over s minus 1 minus 4 inverse transform 1 over s plus 2, and of course the other one on t. And if you remember this, this is not something we have to look up. We know it's just e to 1t, or if you look it up at the table, that's what you'll find. And for the second one is e to a negative 2t. So you see, that's the solution for this IVP. And as you see, we didn't go into a general solution, then apply the initial conditions to get to this. Alright, let's do another example. Okay, so now follow the same thing. So maybe I'll give you kind of the main steps on this one, because you want to follow. It's a similar example as the previous one. So what would you do? You would take Laplace transform to both sides, right? Then with linearity, it's going to be Laplace transform for the second derivative there, which gives you this. And of course on s, right? Minus s, of 0, of 0. Then on the first one, you get s, Laplace transform, minus y of 0, minus 10, y over s equals 0. And then you will do the same math on all this stuff, and you'll collect the terms and all that. So let's say I'll give you the next step. Once you work on this, you should get s squared times y of s plus 2s minus 11, which comes from the initial condition. Alright, so this is kind of the next step. Then you're going to combine some numbers here. I actually gave you the next one, so maybe I should give you when after it's multiplied. Yeah, once you distribute. Once you distribute, that's what you get. And what's next? So then we are going to collect the terms that have the y of s, and we get s squared minus 3s minus 10 equal negative 2s plus 17. Alright, so y of s is negative 2s plus 17 over s squared minus 3s minus 10, which definitely factors to negative 2s plus 17 over s minus 5 and s plus 2. Similar work, the Heaviside cover-up works on this, so you can do a over s minus 5 plus b over s plus 2. So I want you kind of to practice that, cover one and do the other and see what values you get for a and b. So use the same method as the previous example, and you should get 1 over s minus 5 negative 3 for b s plus 2, and now we are in the last step. Is take the inverse transform on these. The first one doesn't have a multiple, so it is what it is. The other has a multiple, and this is y of t. Of course, these are going to be on t. One over s plus 2. Of course, these are on t. So the solution is going to be y of t equal to e to 5t, the exponential function of 5t here, minus 3 times exponential function of negative 2t. Okay. Alright, we do let's do one with having something on the right side. Why not? Let's see example. Here is the IVP less than y prime. It's similar work. Initial conditions. So we're going to take Laplace transform to both sides, and now you have, let's see, did I show it? Of course on, yeah, okay, it's good. Alright, so here what's different is, of course, Laplace transform on the right side here is we have a function, which is fine. We know how to do this. 33 linearity, we're going to bring it outside. And we know that this is for on S is just going to be 33 times 1 for this function S minus 2. Alright, So you're going to do now on the on the left hand side, just like we did before. So let's do for the second derivative. Then next, the first derivative. Equal to 33 over s minus 2. We'll collect the terms that have y of s, as we did before, and we factor, then you get this factor here, and we move everything to the right hand side. From the left hand side to the right hand side, we get negative 4s plus 31 minus 40 plus 33 over s minus 2. Okay, so let's make these as a fraction. So combine them. Negative 4s, you're gonna time by s minus 2, and combine 31 with negative 40, then you do times s minus 2 for common denominator. Try it and you should get negative 4s squared minus s plus 51. Of course, there. Then you're going to divide by this thing here. Okay, so try it and you should get, and of course this s squared plus 10s plus 9. To factor two numbers multiply to 9, add up to 10 is 9 and 1. Alright, so you should have negative 4s squared minus s plus 51 over the s minus 2, and it is, but you divide by this s plus 1. Let's do a different color just so it doesn't mix up, blend with the other one. So s plus 1 and s plus 9. So you divide by them, s plus 1 times s plus 9. Alright, and if you look into the fraction decomposition, this is just like the other examples we did. So we can still do, let's say, s plus 9 and a, and let's say I pick s plus 1 and next, then b, and c for s minus 2. The heavy side cover-up works on this, just like the other ones I did. And so you can have a as negative 3, and you'll find that b is negative 2 and c is negative 1. So try it, check, double check, see if you get these. Alright, so that makes y of s to be negative 3 over s plus 9 minus negative 2 over s plus 1 plus 1 over s minus 2, and use the inverse Laplace transform. We've seen it now a few times, so we know how it works. Negative 3 times the inverse transform of 1 over s minus 9. So that's s plus negative 9, so that makes it negative for the t there. And this will be negative 1. And this one would be 2. Alright, we can fit one more example. and this one will go quick because you'll see why. These IVP we have again something that's not zero on the right hand side, but you see that you will actually go quicker and you will help us understand more. Alright, so we know we take Laplace transform to both sides. For second derivative, Laplace transform on it will give us this. Then 5 for y, Laplace transform on y is just going to be the function y of s. And then Laplace transform for t cubed, when you check the table, you'll see that you do n factorial, which is 3 here, and then you do n plus 1, which will give you 4 here. Right, so 6 over s power 4. These are, let's say, these are 0, so that leaves us with s squared plus 5 equal 6 over s power 4, and y of s is 6s power 4 times s squared plus 5. And I think in this question that one was requested. So always keep attention, of course, to the instructions to what it is that is asked, whether you're looking for a solution or you're looking just to express the intermediate step here. And all right, I think that does it for this section. If I look into other examples, I could do some that stretch a little more than these, involving maybe partial fraction decomposition, other cases where the heavy side cover-up will help with the start of the problem, but it won't help throughout finding, let's say, A, B, C, D, or something like that. It will help you with the beginning. Of course, you always have that method that is learned before, using the system of equations to solve, or giving some values for S to start with and figure out the solution. But I'll check those and maybe post a video about them. Thank you.